Welcome everyone. I'm excited to kick off today's presentation with the topic of sound. In this first slide, I want to warmly welcome you all and give you a quick overview of what we'll be exploring. We'll look into the fascinating world of sound, its properties, and how it impacts our lives. So, let's dive in and get started. Let's take a closer look at the contents of this presentation. First, we'll explore how sound is produced and the nature of sound waves. Then, we'll see how sound propagates through different mediums, focusing on air. We'll also discuss the characteristics that define a sound wave, such as frequency and amplitude. Understanding how sound reflects and echoes helps us grasp phenomena like sonar. Another key point is the range of human hearing, which varies from person to person. We'll also look at ultrasonic sound and its applications, especially in technology like sonar. Finally, we'll examine the structure of the human ear, which is essential for our ability to perceive sound. All these topics connect to give us a comprehensive understanding of how sound works, how we detect it, and how it's used in various practical ways. Let's talk about how sound is produced, which is a key part of understanding sound itself. Sound is created when objects vibrate. Now, vibration is essentially the rapid back-and-forth motion of an object. This motion is what generates sound waves that travel through the air or other mediums. For example, think about the human voice. When we speak or sing, our vocal cords vibrate, and that vibration creates sound. Similarly, if you pluck a stretched rubber band, it vibrates and produces a sound. These vibrations are fundamental because they are the direct cause of the sounds we hear. So, in essence, whenever an object vibrates, it sets off a chain of events that results in sound. This is a basic but crucial concept because it connects the physical movement of objects to the sounds we perceive, tying into the overall idea of how sound is produced and transmitted. Let's try an interesting activity. First, take a tuning fork and strike its prongs gently on a rubber pad. Once it's vibrating, bring it close to your ear. What you'll notice is that you can actually hear a sound. This demonstrates that vibrating objects produce sound waves. Now, to see this in action, hold a suspended table tennis ball nearby. When you touch the vibrating prong to the ball, you'll see the ball being pushed away repeatedly. This movement shows us that the vibration from the tuning fork is transferring energy to the ball, causing it to move. And that's a clear example of how vibrations are directly responsible for sound production. This activity really helps connect the idea that vibrations create sound waves, which is a key concept in understanding how sound works. Let's explore how sound propagates through a medium. When a vibrating object produces sound, that sound wave travels through a medium. This could be solid, liquid, or gas, and eventually reaches our ears. Now, what's happening at the particle level? When the object vibrates, it causes the particles around it to vibrate as well. The particle in direct contact with the vibrating object gets displaced from its resting position first. This displacement then exerts a force on the neighboring particle, which in turn gets displaced. After pushing the next particle, the first particle returns to its original position. This cycle repeats through the medium, creating a wave that carries the sound forward. It's important to understand that the particles themselves don't travel with the wave. Instead, they vibrate in place, passing the disturbance along. This movement of energy through the medium is what we call a wave, a disturbance that moves through the medium by the vibration of its particles. Because sound relies on these particle vibrations, we classify sound waves as mechanical waves. So, in essence, sound is a wave that propagates through a medium by vibrating particles, and this process allows us to perceive sound across distances. Let's talk about how sound propagates through air, which is actually the most common medium we experience daily. When a vibrating object, like a guitar string or a vocal cord, moves forward, it pushes against the air in front of it. This pushing creates a region of high pressure called a compression. Think of it as a ripple of tightly packed air molecules moving outward from the source. Then, when the object moves backward, it creates a low-pressure area known as rarefaction, where the air molecules are more spread out. As this object continues to vibrate back and forth rapidly, it generates a continuous series of compressions and rarefactions. These alternating high and low pressure regions travel through the air, carrying the sound away from the source. This process of compressions and rarefactions is fundamental to how sound moves through the air and reaches our ears, helping us perceive the sounds around us. It's a great example of how simple physical movements can produce complex sensations like hearing. Sound, as you might know, is a mechanical wave, which means it needs a medium to travel through. Without a medium, sound simply can't move. It travels through solids, liquids, and gases, each offering different ways for the sound waves to propagate. For example, when you speak, your voice travels through the air, which is a gas. But if you knock on a table, the sound travels through the solid material of the wood. Interestingly, sound cannot travel through a vacuum, like space, because there's no medium for it to move through. This concept is fundamental because it explains why we hear sounds only when there's a medium present, and it ties into the broader theme of how energy moves through different environments. Let's look at this interesting activity. We start by suspending an electric bell inside an airtight bell jar. Then, we connect the bell jar to a vacuum pump. Now, when we press the switch, you can hear the sound of the bell. That's because the air inside the jar transmits the sound waves to our ears. But here's the key part. If we pump the air out of the jar using the vacuum pump, suddenly we can't hear the bell anymore. This clearly shows us that sound needs a medium, like air, to travel through. Without it, in a vacuum, sound cannot propagate. This experiment highlights the essential role of a medium in sound transmission, connecting to our broader theme of understanding how sound works. Now, let's explore how sound waves travel through a medium. If you take a slinky and stretch it out, then push and pull one end back and forth, you'll see how the wave moves along the slinky. This simple activity helps us understand that sound propagates as a series of compressions and rarefactions. The key point here is that, in these waves, particles move back and forth in the same direction as the wave is traveling. These are called longitudinal waves because the particle motion is parallel to the wave's direction. It's also interesting to compare this to transverse waves, where particles oscillate up and down, perpendicular to the wave's direction, like ripples on a pond. Recognizing these differences helps us understand the nature of various wave types and how they behave in different media. Connecting this to our overall theme, understanding the distinction between longitudinal and transverse waves is crucial for grasping how different types of waves, including sound, behave in the physical world. Let's take a closer look at the characteristics of a sound wave. Sound waves can be described by three main properties: frequency, amplitude, and speed. These properties help us understand how sound behaves as it travels through a medium. Graphically, we can visualize sound as a wave, where the changes in density and pressure are evident as the wave moves. When the particles in the medium get crowded together, we call that a compression. Compressions are regions of high pressure and high density, and if you look at the wave, these are represented by the upper parts, called crests. On the flip side, when the particles are spread apart, we have what's called rarefactions. These are low-pressure, low-density regions, and in the wave diagram, they appear as the lower parts or troughs. Now, an important concept is the wavelength, which is the distance between two consecutive compressions or two consecutive rarefactions. This measurement helps us understand the wave's length and is symbolized by the Greek letter lambda, lambda. The SI unit for wavelength is meters. Understanding these features, the compressions, rarefactions, and wavelength, helps us grasp how sound propagates and how different properties of sound waves influence what we hear and measure. These characteristics are fundamental to analyzing sound in various contexts, from music to medicine. Let's talk about the frequency of sound waves. Frequency essentially refers to how many sound wave cycles pass a point in 1 second. It's measured in hertz, or Hz. The higher the frequency, the more cycles per second, and this typically corresponds to higher-pitched sounds. Conversely, lower frequencies mean fewer cycles per second, resulting in lower-pitched sounds. This concept is crucial because it helps us understand how we perceive different sounds, from the deep bass notes to the high-pitched whistles. Throughout this presentation, we've seen how frequency influences the quality and perception of sound, connecting it to everything from music to communication. So, understanding frequency is key to grasping how sound waves carry information and evoke responses in us. Let's talk about the time period of a sound wave. The time period is basically the time it takes for the medium's density to go from a maximum to a minimum, and then back to a maximum again. In other words, it's the duration of one complete cycle of oscillation. Think of it as the time for one full vibration or oscillation in the medium. This is represented by the letter T. The unit for the time period is seconds, which makes sense because we're measuring a duration. Now, an important relationship to remember is between the time period and the frequency of the sound wave. The frequency, denoted by the symbol nu, is how many oscillations happen in 1 second. The time period and frequency are inversely related, and we express this mathematically as T equals 1 divided by nu, or T equals 1 over nu. Similarly, if we know the time period, we can find the frequency by taking the reciprocal. Connecting this to the overall theme, understanding the time period helps us grasp how sound waves propagate and how quickly they oscillate, which is crucial for analyzing sound behavior and characteristics. Let's talk about wavelength and amplitude. The wavelength is essentially the distance between two consecutive crests of a wave. Think of it as the space from one high point to the next high point. Now, amplitude refers to how tall these crests are, which tells us about the wave's energy. The higher the crest, the greater the amplitude. Focusing on sound waves, the amplitude is the maximum disturbance or displacement in the medium, like air, on either side of the mean or rest position. You can also think of it as the height of the crest or the depth of the trough. We typically denote amplitude with the letter A, and interestingly, the SI unit for amplitude is the same as that for density or pressure, which makes sense because they all relate to the energy or intensity of the wave. Understanding these concepts helps us grasp how sound behaves and how its energy is transmitted through a medium. So, when you're listening to loud music or a whisper, it's really the amplitude that's changing, affecting how loud we perceive the sound to be. Let's take a closer look at how wavelength, frequency, and pitch are related. Since sounds travel at about the same speed, the wave with the shorter wavelength will pass by more frequently. This means it has a higher frequency, which we perceive as a higher pitch. So, in simple terms, a higher pitch sound is produced by waves with shorter wavelengths. Now moving on to amplitude, which is all about loudness. The amplitude is basically the size of the wave, specifically how much it peaks at the high points. The larger the amplitude, the more energy the wave carries, and the louder the sound we hear. Think of it like how big a splash is, bigger splash, louder sound. Next, let's connect pitch and loudness to their underlying factors. The pitch of a sound, whether it's shrill or flat, depends on the frequency of vibration. When the frequency is high, the pitch sounds high, like a whistle. When the frequency is low, the pitch is low, like a drum. Loudness, on the other hand, depends on the amplitude. A bigger amplitude means the wave has more energy, resulting in a louder sound. Conversely, a smaller amplitude produces a softer sound. Understanding these concepts helps us see how the physical properties of waves shape the sounds we experience every day. The speed of sound varies depending on the medium it travels through. In general, it moves faster in solids, slower in liquids, and slowest in gases. This is because the particles are more tightly packed in solids, which allows sound waves to pass through more quickly. Additionally, the temperature of the medium plays a significant role. When the temperature increases, the particles move more rapidly, and as a result, the speed of sound also increases. Now, relating this to the fundamental relationship, we have the formula speed equals wavelength times frequency. This means that if we know the wavelength and the frequency of a sound wave, we can determine its speed. Understanding these factors helps us grasp how sound behaves in different environments, which is essential in fields like acoustics, communication, and even engineering. So remember, both the type of medium and its temperature influence how fast sound travels. Now, let's talk about the reflection of sound. Just like light, sound waves can be reflected when they hit the surface of a solid or a liquid. This means that sound can bounce off surfaces, which is important in many applications, from sonar to acoustic design. The key point here is that the laws of reflection apply to sound as well. So, the angle at which the sound wave hits the surface, known as the angle of incidence, is equal to the angle at which it bounces off, called the angle of reflection. Another important aspect is that the incident ray, the reflected ray, and the normal line, which is perpendicular to the surface, all lie in the same plane. This is a fundamental concept because it helps us understand the geometric relationships when sound waves reflect. Connecting this to the overall theme, understanding how sound reflects allows us to better grasp how sound travels in different environments, whether it's in a concert hall or underwater. It's all about how waves interact with surfaces, shaping how we perceive sound in our world. Let's try an interesting activity to understand how sound waves behave. Take two pipes of the same length and place them on a table near a wall or a metal plate. Now, keep a clock near the open end of one pipe. What you'll do next is try to hear the sound of the clock through the other pipe by adjusting its position. As you move the pipe, pay attention to how the sound reaches you. The key here is to measure the angles of incidence and reflection. What you'll find is that the angle at which the sound wave hits the surface, the incident angle, is equal to the angle at which it bounces off, the reflection angle. This demonstrates a fundamental principle. The incident ray, the reflected ray, and the normal all lie in the same plane. This activity helps us visualize how sound waves reflect, and it directly connects to the broader concept of wave behavior, showing that reflection follows predictable rules similar to light. It's a simple yet powerful way to see these principles in action. Let's talk about echoes. When we shout or clap near something like a tall building or a mountain, we often hear the same sound bounce back to us. That repeating sound is what we call an echo. It happens because the sound waves reflect off the surface and travel back to our ears. Now, for us to hear a clear echo, there needs to be a certain time gap between the original sound and the reflected sound. Specifically, at least 0.1 seconds should pass. Given that the speed of sound in air is about 344 meters per second, we can calculate how far sound travels in that time. Multiplying 344 meters per second by 0.1 seconds gives us approximately 34.4 meters. But here's an interesting point. Since the sound has to travel to the reflecting surface and back, the surface needs to be only half that distance away to produce a clear echo. So, that minimum distance is about 17.2 meters. This concept ties into how sound waves behave and how we perceive echoes, which is important in understanding acoustics and designing spaces with good sound quality. Reverberation is a fascinating aspect of sound. It occurs when echoes are heard more than once, which happens because sound waves bounce off multiple surfaces. This repeated bouncing creates a persistence of sound that we call reverberation. In large spaces like halls or auditoriums, this can become quite noticeable and sometimes overwhelming. To manage this, architects and designers use sound-absorbing materials on the ceilings and walls, such as compressed fiber boards, rough plaster, or draperies. These materials help reduce the reverberation, making speech clearer and music more enjoyable. So, understanding reverberation is really key to creating spaces that sound good and are comfortable for audiences. Let's talk about some interesting uses of multiple reflection of sound. You might have noticed how doctors listen to our heartbeat using a stethoscope. The sound from the heart reaches their ears partly because of multiple reflections, which helps amplify and direct the sound so they can hear it clearly. Now, think about megaphones, horns, and musical instruments like trumpets or shahnais. These are designed to send sound in a specific direction through multiple reflections, instead of spreading the sound everywhere. This focused reflection helps project the sound much farther and more clearly. Moving to larger spaces, like cinema halls and auditoriums, their ceilings are often curved. This clever design ensures that sound waves bounce around through multiple reflections, reaching every corner of the hall. Sometimes, A curved soundboard is placed behind the stage to help spread the sound evenly across the entire space, making sure everyone hears clearly. So, as you can see, multiple reflection of sound isn't just a physical phenomenon. It's a key principle used to enhance sound quality and projection in many practical applications, tying back to our overall understanding of sound behavior. Let's talk about the range of hearing in humans and animals. Humans can hear sounds with frequencies between 20 Hz and 2000 Hz. Frequencies below 20 Hz are called infrasonic sounds. Interestingly, some animals like dogs, elephants, rhinoceroses, and whales not only produce infrasonic sounds, but can also hear them. These low-frequency sounds often travel long distances and are used for communication over great ranges. On the other hand, sounds with frequencies above 2000 Hz are known as ultrasonic sounds. Many animals, including dolphins, bats, rats, and porpoises, produce and hear ultrasonic sounds. What's fascinating is how some animals, like bats, use ultrasonic sounds to navigate and hunt. They emit these high-frequency waves, and by listening to the echoes that bounce back, they can detect obstacles and even locate prey with incredible precision. This process, called echolocation, is a perfect example of how different animals adapt their hearing abilities to their needs and environment. Connecting this to the overall theme, it really highlights the incredible diversity of hearing capabilities across species and how sound plays a vital role in their survival. Ultrasonic sound has a variety of practical uses that really highlight its importance in different fields. One common application is in cleaning objects like electronic components. The process involves placing these components in a cleaning solution, and then ultrasonic waves are sent through the liquid. Because these waves are at such a high frequency, they cause dirt and grime particles to detach from the surfaces, effectively cleaning even the tiniest crevices. Another significant use of ultrasonic sound is in medical imaging, specifically in ultrasound scanners. These devices send ultrasonic waves into the body, which then bounce back from internal organs. The scanner uses these reflected waves to create detailed images, helping doctors diagnose and monitor conditions without invasive procedures. Ultrasound is also crucial in industrial settings, such as detecting cracks in metal blocks. By sending ultrasonic waves through the metal, any cracks or flaws reflect some of the waves back, alerting us to structural issues that might not be visible on the surface. This non-destructive testing method is vital for ensuring safety and integrity in engineering. And in the medical field, once again, ultrasonic sound is used to break down small kidney stones into finer pieces. These tiny fragments can then be passed out of the body naturally through urine, providing a less invasive way to treat kidney stones. All of these examples show how ultrasonic sound is a versatile and valuable tool across different industries, connecting back to our overall theme of understanding how sound waves can be harnessed for practical benefits. Let's talk about sonar, which stands for sound navigation and ranging. It's a fascinating device that uses ultrasonic waves to measure things underwater. Essentially, it helps us determine the distance, direction, and speed of objects beneath the surface. A typical sonar system has two main parts, a transmitter and a detector, both installed on ships. The transmitter sends out ultrasonic sound waves into the water. These waves travel through the water until they hit an object, like the seabed or a submerged object. When that happens, the waves bounce back and are received by the detector. The key idea here is that by knowing how fast sound travels in water and measuring the time it takes for the waves to travel to the object and back, we can figure out how far away the object is. So if we call the total time for the round trip t and the speed of sound in water v, then the distance to the object, d, can be calculated using this simple formula. 2d equals v times t. Or, put another way, d equals v times t divided by 2. This is fundamental because it allows us to measure underwater distances accurately, which is crucial for navigation, mapping the seabed, or detecting objects beneath the surface. It connects directly to our overall theme of underwater exploration and sensing technologies. Let's take a closer look at the structure of the human ear. It all starts with the outer ear, which is called the pinna. The pinna's main role is to collect sound waves from our environment. These sound waves then travel through the ear canal toward a thin membrane known as the eardrum. When the sound waves hit the eardrum, it begins to vibrate. These vibrations are then amplified by 3 tiny bones in the middle ear, commonly called the hammer, anvil, and stirrup. This amplification helps us hear more clearly. The middle ear then passes the sound vibrations to the inner ear. Inside the inner ear, the cochlea plays a vital role by converting these vibrations into electrical signals. These signals are sent to the brain via the auditory nerves. And finally, our brain interprets these signals as the sounds we recognize and understand. This entire process highlights how complex and finely tuned our hearing system truly is, connecting the physical sound waves to the meaningful sounds we experience daily.